This is the start of Chapter 3. In Chapter 3, we basically wrap up everything that we've been doing with derivatives and everything that we're going to do with derivatives and everything that we have done in math from the beginning of time to now. We're going to spend the next few weeks on this, and actually it will probably take us all the way up to just about the end of the semester. So this chapter does take a while to get through. There are lots of sections to cover. There's lots of topics to talk about. There's lots of theorems that we're going to learn about that you need to know. And you need to be familiar with them and be able to work with them at like the drop of a hat, basically, so to speak. So we're concluding our learning about derivatives and differentiation. And I already talked about that. Determine how functions behave over intervals. This is how we're going to start off. Learn how to sketch curves by hand. That's how we're going to finish up. And apply our knowledge to real-world optimization problems. That is the end of the chapter. And it's very exciting times when we get there. Maximize and minimize things, yeah. So in Algebra 2, you learned about optimization using linear programming. And we're going to do something fairly similar to that, except it's not going to be necessarily optimizing cost or profit or anything like that. It's going to be optimizing space or optimizing amount of materials used, things like that. It's actually fairly exciting. I think it's kind of interesting, and it's a good branch of mathematics to know how to do. So, with all of that being said, I've got some vocab for you. Wouldn't be a section in calculus if we didn't have a bunch of new words to learn. So, first of all, extrema. Extrema is plural for something else. Extreme values on an interval. Usually we're talking about a maximum or minimum value. So when you see the word extrema, we're talking about potentially both maxima and minima. Do I have those words up here anywhere? No, it doesn't look like it. So minimum is a single minimum, but minima would be plural. Maxima would be plural for maximum. So we could be talking about maxima and minima together. We could just be talking about a minimum or a maximum, but that's what extrema means. The absolute minimum would be the absolute smallest value of a function over some interval. So it's not like over the entire existence of the x number line. It's just over some little interval, potentially. The relative minimum would be just a low point, or a value that occurs locally on an interval, but not the absolute minimum. It can be, it doesn't have to be. So if we take a look at this ridiculous looking graph that we have here, this is the function, incidentally, that makes that graph. Over an interval, so I'm just going to pick an interval here. I'll go from 0, and I'm using these brackets here to indicate that I'm including 0, and I'll go all the way out to pi. So my interval will be from 0 to pi on this graph that I'm looking at. Then that means that to find an absolute minimum, I need to find the absolute lowest point on that graph. And we'll talk about in a little while how my inclusion of these numbers here actually includes those as potential areas for a absolute minimum. So all I have to do on this graph really is just look for the absolute lowest point, and it seems to be right there. So that would be the absolute minimum. Relative minimum would be where I have little valleys going on. So a low point or a valley that occurs locally on an interval, but it's not necessarily the absolute. So this would be a relative minimum, so would this, so would this, so would this. Okay? Absolute maximum would be the largest value of a function over an interval, so kind of like the valleys of the minimums. The peaks of the function will be your maximums. This would be your absolute maximum right here, over that interval anyway. And then the relative maximums, very similar to relative minimums, any high point that occurs locally but is not necessarily the absolute maximum. So this would be a relative max, this would be a relative max, this is a relative max. Technically, because I have a closed interval here with that bracket, I also need to consider the endpoints. This would be a local max or a relative max right here also. This over here with that closed interval would also be a relative minimum, just because of that closed interval. If it was an open interval, then we would not include those endpoints. We'll talk about that as the chapter goes on. Actually, I think in this section. Okay, remember your interval notation. I've already been talking about the brackets. An open interval uses parentheses. A closed interval uses those brackets. And take a look at the graph. Describe it using the vocab. I've already explained all that stuff. So based on the graph, what is true at all extrema except for at the endpoints of an interval if we're talking about a closed interval? Slope 0. Yeah. So without even going into the section any farther, if I'm asking you where the extrema of a function are, what will you want to do? You're going to take the derivative and set it equal to 0 and solve. Yep. So that will be how you find all of your relative extrema. You already got the whole, basically, half the chapter down if you understand that. Our first theorem that we're going to learn in chapter 3, and there are a lot of them, is called the extreme value theorem. And it says, I'll just read it to you before I explain it. If a function is continuous over a closed interval, then the function has both a minimum and a maximum over the interval. So that's the wording. We need to kind of dissect this a little bit. First of all, it says a closed interval. A closed interval means brackets. And that means that I need to include the endpoints of that interval in my little analysis that I'm doing. If this is the case, then the function has both a minimum and a maximum over that interval. Take a look at the graph. I'm giving you a closed interval from -1 to +3. Well, -1 is right here, and +3 is right there. Do we have a maximum and a minimum in this? Yeah, we do. So we have a maximum clearly right here. This would be a relative maximum. Because of this closed interval over here, as this thing comes up, we also appear to have a relative maximum here. As this thing travels downward over to the interval on this side, we go down to our function, we appear to have a relative minimum here because of that closed interval. If that was an open interval, we wouldn't need to worry about this one here. We wouldn't include it. But we also definitely have a relative minimum here. So clearly on this particular function, there's definitely a minimum and a maximum over the interval. Okay? So the question is, how can we determine what those maxima and minima are over this interval algebraically? Take the derivative of the function. So let's say we do that. We get f prime of x equals 3x squared minus 6x. Now what do? We want to find where the slope is equal to 0 because obviously here and here the slope of the tangent line would be 0. So we set it equal to 0, and now we can divide everything by 3, and we get x squared minus 2x equals 0. Now what? Factor out the GCF, which is x times x minus 2 equals 0. Use the zero product property, solve for x. You get x equals 0, x equals 2. Take a look at the graph. X equals 0 is right here. X equals 2 is right here. So we found where those two things have the maximum and minimum. Okay? These would be definitely extrema, but we don't know if they're absolute or not. Not only that, but if we don't have the graph in front of us, we don't even know if they're maximum or minimum. Right? The only reason we know that is because we're looking at the graph.
So then they're just classified as extrema?
They're just extrema at this point, yeah. So that's how we would find the x coordinates. Then to find the y coordinates, we would take these values and substitute them back in. So obviously if I do that, I have an extreme value at 0, 0, and also another one at, if I take 2 and plug it in, I get 8 minus 12, negative 4. So 2, negative 4. 0, 0, definitely. 2, negative 4, definitely. Okay? Now the next thing that you would want to do is, because this is a closed interval, you would want to substitute in the endpoints of the interval to find more ordered pairs. So the endpoint here would be negative 1, negative 1 cubed is negative 1, negative 1 squared is 1, so negative 1 minus 3 is negative 4. So negative 1, negative 4 is one endpoint of my interval. And this is really sloppy the way that I'm doing this. I'll show you how to do this better in a little bit. Substitute in that 3, so I'd have 3, that'd be 27, minus 27, which is 0. So 3, 0 is my other endpoint. So now from this, I can say that this 0 is bigger than that, negative 4 is bigger than that, negative 4 is the same as that 0. So these are relative maxima here, and these are relative minima. Okay, without even looking at the graph. That's kind of where we're going to go from here. So here's where we're at. Maximum and minimum values occur when we have a peak or valley, or at endpoints if we have a closed interval. They also occur at vertical asymptotes and sharp points. Think about that one for a second. If I have a vertical asymptote, then my graph does something like that. Maybe it comes back down. Okay? Obviously, this thing is going off towards a maximum value of infinity there. Sharp points, maybe I have a graph that does something like that. This is also going to be a relative maximum here. Or I have a graph that maybe does something like this. So in this case, I would have a nice relative minimum that I could probably calculate pretty easily. But here, this is going to be a sharp point. That is a relative maximum. And we know that we can't take the derivatives at sharp points, so we're going to have some interesting things going on there. We give a special name to these places on a function. These things that we found, like in the last problem and the things that I've been pointing out to you on these problems, are called critical numbers. Critical number is any place on a function where, the function f, where f prime at that number is equal to 0. So in other words, critical numbers are where the slope of the tangent line is equal to 0, the x-coordinate of where the slope of the tangent line is equal to 0. Or if the function is not differentiable at that number, that is also a critical number. So the function would not be differentiable at a vertical asymptote. The function would not be differentiable at sharp points. Those are also critical numbers. Places where you have division by 0, critical numbers. These are the x values, the values of the function that produce extrema. If you are asked for locations where is the relative minimum or maximum, that you will need ordered pairs. So if I'm just asking for critical numbers, I'm just looking for the x values that produce extrema. If I want the locations of the extrema, then that means you need to give me ordered pairs. Very important point right here, relative extrema only occur at critical numbers. They will not occur anywhere else. However, absolute extrema can also occur at the endpoints over an interval. So if I'm asking for relative extrema, or if I have an open interval, then you only need to find your critical numbers. But if I have a closed interval, I'm asking for absolute extrema, then you need to also consider the endpoints of the interval, like we did in that previous problem. So you have a little list here, how to find extrema on a closed interval. These are your guidelines, important safety tips for survival in calculus, chapter 3. Look for vertical asymptotes. Those are automatic critical numbers. Places where you have division by 0, automatic critical numbers. Take the derivative of the function. Find the critical numbers, meaning set the derivative equal to 0. And then evaluate the original function at those critical numbers that you found to find your extrema.